Okay, time for a new electrophile. This electrophile is borane, BH3, the fifth element, not Mila Jovovich. That's an excellent movie, though. I highly recommend it if you are stuck at home. Here we're going to see how boron is going to react as an electrophile. How do I know boron is an electrophile? I know that because boron takes 3 bonds. I don't have a periodic table to gesture to right now, but if you look online or in your textbook, you will find that boron is in the column before carbon, and so it only has 3 bonds. So it's actually short an octet. We can think of this as a very good electrophile. Another way to think about it is as a Lewis acid. It is an electron acceptor. Okay, so what does that look like in our case? Well, let me show you a way that I think about or model this reaction, the mechanism that I think of. And after that, I'll show you that that's not quite right, and the actual mechanism is a little bit more complicated. But first, let's come at it the easy way. I am still going to think of alkenes reacting as kind of like they did before, right? So this is my electrophile. The door swings out and grabs some electrophile, in this case boron. What does that give me? Well, that would give me a cation over here, just like before, right? Just like when we added HBr. And now I've got a negatively charged boron. Right? So before, boron had 3 bonds. Now it's got 4, so it's got a negative charge. Okay? So I've got this positive charge thing here and a negative charge thing here. So it seems like it would make a lot of sense for this hydrogen and its electrons to move over to that carbon. Right? So before this had 1 H, and now it has 2 H's, because this hydrogen is now over there. Okay? Does it actually work this way? Not really. What actually happens is that all of this happens at the same time. So this double bond swings out and grabs boron, and these bonds are transferring at exactly the same time. You end up with the same product. So again, this is how I think about it, but this is how it actually goes. Okay? So why would I want these boranes? Well, first of all, this will actually happen 2 more times. So this is still boron with 3 bonds, just like this is. Okay? And so it'll actually go through this process twice more. Until I have alkyl groups hanging off of my borane like this. So again, I've got essentially 3 molecules of alkene plus 1 molecule of borane giving me this. Okay, why might I want this? Well, let me erase this and we'll talk about it. Boranes. What are they good for? Absolutely nothing. Usually these things are not very stable even. So even if we had wanted to keep them, we couldn't. But there is a few cool things that they do, and one very cool thing in particular. If I treat this borane that I've made just in the same pot, I don't have to isolate it or anything. If I treat it with hydrogen peroxide and base, so sodium hydroxide. Hydrogen peroxide is actually a better base than OH minus is, or a better acid than water is, rather. So what I end up with is this peroxide base, or ooh. This is a good nucleophile. It's a great nucleophile. And this is still a good electrophile. So what's going to happen is I'm going to form I'm going to form a borate. So boron with 4 bonds, negative charge, and this cool OOH coming off of it. So now the magic happens. And this is something that I would not expect you to memorize as we learn mechanisms. So a lot of mechanisms I'll ask you to learn in this class. This is one of the few where you can just appreciate it for its beauty. But check it out. We've done hydride shifts in the past. This is kind of like that. So one of these boron-carbon bonds is going to go up to this oxygen. I'm going to break this really weak OO bond. OO bonds are always very weak. So that is going to make that leave. And I'm going to end up with this thing with the BO bond now. So notice, before I had carbon-boron bond, now I have a carbon-oxygen bond. Okay? This will happen 2 more times until all the alkyl groups have moved. Onto boron. And now, plain old hydroxide will hydrolyze all of that, essentially giving me borax on one end and 3 alcohols. So, cool. Now I know a new way to make alcohols. Remember, we already know one way to make alcohols. If we take an alkene and react it with catalytic acid in water, we go through the carbocation to get this Markovnikov alcohol. The more substituted end of the alkene gets the OH. In this reaction, if I treat it with BH3, and usually I would use something called BH3 etherate, or BH3.THF. So this is just a more stable form of BH3. So it's a Lewis acid, Lewis base pair, but don't need to worry so much about that. This just acts like BH3. Anyways, if I take an alkene, react it with BH3, and then peroxide and base, what I just laid out is that I will get the less substituted alcohol, the other alcohol. All right, so not the Markovnikov alcohol. We need to come up with a name for this one. Let's call it the anti-Markovnikov, because we are entirely bereft of creativity. Okay, so this is fantastic. Remember, if I'm a drug chemist, I want a lot of control over what I can make. Sometimes I want to make the more substituted alcohol. Sometimes I want to make the less substituted alcohol. All right, and I can now have my choice because I know 2 different reactions. Do they go by different mechanisms? Yes, kinda, but in both cases, what drives the regioselectivity, right? Regioselective means it will only add to one area of the molecule. What drives the regioselectivity of this is that I will always want to have more positive charge on this internal carbon and not on the end carbon. All right, so here that manifests as the full cation. Down here, this manifests as this carbon in the transition state is going to be more positive because this carbon is giving up its hydrogen. So I have the negative boron over here, the positive carbon over here. So in both transition states, or in both intermediates, I've got that positive charge on that internal alkene, not on the end of the alkene. 2 different ways to make alcohols. Nice.